Today's speaker is Dr. Barış Burnak. I am grateful for his contribution. Actually, his short biography, let me give his short biography, then I'm going to let him have the stage. Barış obtained his bachelor's and master's degrees in chemical engineering from Bogazici University and Ph.D. from Texas A&M Universities. His research focused on developing mathematical modeling techniques for integration of process design, scheduling, and control problems. He is currently employed at Phillips 66 as an research and development engineer. By the way, what's that 66? It sounds ominous.
That has a lot of story. I think they tested the first gasoline on Route 66, which is the historical roads in the US. And I think it had an octane number of 66 and a couple of more reasons that I can't remember now. So they just thought that would be a fun fact to do.
Okay, interesting. As a research and development engineer, in his free time, he explores a number of chess games he can lose consecutively. Probably he's a good chess player. Actually, I didn't know that. But now let him have the word. Yes, stage is yours, Dr. Burnak.
So I cannot share my screen.
Oh, okay, yes.
Disabled participants.
My bad. I'm going to. Now you should be able to share a screen.
Let me try again. Okay, I hope you can see it now. Is that good? Can you see it?
Yes, 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 we can see it. Okay. Yes, yeah.
Okay, so once again, thank you for the introduction. And before I start, I would like to just say that it's very nice to be back, although it is just virtual, but now it's very exciting and new for me to be back as a speaker this time, but not as a student. I'm going to talk about today mostly about my PhD studies, which I finished about more than a year ago. And I tried to structure this talk in such a way that everyone from all expertise can follow, can get something from it, hopefully. And I hope you'll enjoy it. So I tried to condense my whole outline in my title. So I will first start with some classical chemical engineering problems and mostly focus on process design and process control problems. And then I will introduce some more modern mathematical optimization-based approaches and how they can be applied to the classical chemical engineering problems. And then I will showcase this how we can apply these approaches on a binary distillation column, which I hope everyone is more familiar with. And then I will briefly talk about how this will be useful for us, how this all of this mathematical theoretical approaches are actually applicable and they're efficient in industrial applications. So here we go. So as I mentioned, most of my PhD studies revolved around processes. And of course, any process will first start with the design configuration problem. And by design, it will include the processing unit design and also process flowsheet design. These are all part of the design configuration problem. And when we do these designs, we want our process to be able to deliver the the product specifications that we desire. And by doing that, we want it to be able to, economically feasible and be safe and environmental friendly. And once we configure our design, now the next step is to be able to operate it in an optimal fashion, and that is under the umbrella of optimal control. We also know, most of us would know, a more classical PID type of controller, but if we also need to do more advanced constraint problems for optimal control, then we can also consider the optimal control problem, which chemical engineers are also highly engaged in this domain. And lastly, I also considered the scheduling problem, process scheduling problem, in my PhD, which is not necessarily a traditional chemical engineering problem, but in most recent years, especially more and more chemical engineers are engaged in this problem. And what I mean by scheduling is that, let's say you have multiple tasks that can be delivered in multiple units. Like, let's say you have to do multiple reactions, reaction 1 and 2, and you have multiple reactors. So allocating these reactions in the right reactor and the sequencing of these different reactions, all these kind of decisions and the timing, let's say, these are all under the scheduling problem. And optimizing these, the schedule also can improve the efficiency of our problem, which means we will be able to reduce our operating costs. So conventionally, we are all trained to isolate these problems, and we structure these problems in a more hierarchical way. And what I mean by that is we first build our design. We don't necessarily consider the process control problem or the process schedule, but once we have the design, after we build our chemical processes, chemical plants, then we decide on our optimal schedule, and then that schedule will send the control problem the necessary set points and around which steady state point we want to operate at, and then we use the optimal controller. So there is a hierarchical order in between them. And when we do that, we miss the synergistic effect between these different control decisions, different operating decisions. And if we can come up with such a formulation that can encapsulate all of these decisions simultaneously, we can expect improved efficiency from our processes. And that was at the core of my PhD studies. And the whole interaction is, again, throughout my PhD, I focused on merging all of these decisions under a single optimization formulation. And today, I'm going to mostly focus on the design, integrated design and control problem, because I think it's more engaging for the audience, and I hope you will be able to follow that more easily. So this problem is not some unique problem that we came up with, or either me or my advisor came up with. This problem has been studied in literature for close to almost a decade now. And it first started with investigating the steady state flexibility problem, which means that around the steady state point, what is the maximum external disturbance that we can have in our process without any significant disruptions. And that is the steady state flexibility problem. And then the next step was the dynamic flexibility problem, which asks the question, how can I transition from point A, operating point A, to operating point B in a more optimal fashion? And then the controllability problem, when I have these transition profiles, is that going to be actually doable by our controllers? And then more recently, as our modeling tools and our optimization tools improved, now how can we do this in the most economically profitable fashion? So this is a brief summary of the literature. And about 2 years ago, we published a paper on this. And if you're interested, I can share this paper with you. So this is hopefully this gives you an idea on the problem that I researched, and now I'm going to briefly talk about the more modern mathematical optimization tools. And I would first like to motivate you with a very simple question, which can be very complicated to answer. So if you were to ask how many circles you can fit in this box, how would you approach to this problem? So as engineers, we can decompose the problem into constituent subproblems to tackle it more easily. So we can first consider one dimension. We can say, okay, I can fit 2 circles in one dimension, and in the second dimension, I can fit another 2 circles. So that means 2 by 2, I can fit 4 circles. But obviously this is too good to be true, and I deliberately chose these numbers. It's going to be 5 circles, and my message here is that we cannot just always decompose the problem into its subproblems. We may, if we do that, we may miss some synergistic effects between different dimensions. And actually, this whole problem is considered as the packing problem in the optimization community or process systems engineering community. And why, as you can see in this table, which is from the Wikipedia page, as you have more and more circles, or as the diameter of the circle gets lower and lower, the problem gets more complicated. And why is this whole packing problem relevant to our problem? Because what I want to show you is that if we decompose our whole process design and operational optimization problem into subproblems, we may be able to, we may miss some key points that would actually improve our processes significantly. And that was the whole message that I wanted to give. And now, how are we going to make use of this synergistic effects? How are we going to capture this? And that is going to be by mathematical optimization. And let's say as an engineer, you are able to come up with a cost curve as a function of our process variable. Let's say it's the temperature, and you know how our cost, what our cost is going to be as a function of temperature. And now the question is, how are you going to find the best operating conditions, which is obviously going to be this X, but how are we going to find this? Well, we can simply discretize our whole domain, and we can evaluate the functions, and we can compare the results and use the least expensive one, and we can operate at that point. But the problem with that is, first, it is computationally expensive. So if you have a large complex process, you may not be able to evaluate all of these different points. But more importantly for me is that this approach does not guarantee any optimality. So if we will never know if we try further and further if we're going to get any better or not. We have to be happy with whatever we have. So as opposed to this approach, mathematical programming, what people call mathematical programming, provides a systematic approach to compare all of the possible feasible solutions, and it will just return the absolute best solution. So for this simple problem, this is a quadratic curve, so we can simply take the derivative and make it equal to 0, or we can just take, if it is a multidimensional problem, we can just take the gradient of our function and make it equal to a 0 vector and solve the system of equations. So this is more or less the whole idea behind it. And obviously, our real life problems are not going to be as easy as this. And for those, there are a lot of numerical methods, very systematic algorithms. But what is common in all of them is that they provide a mathematical, theoretical guarantee that when you find the optimal solution, it will be indeed the optimal solution. And I will spare you the details of those algorithms, and that wasn't definitely my domain, but you can imagine how these algorithms find this optimal solution is that you can drop a ball on any point on this curve, and you can just observe where it's going to land, where it's going to stop at the end. And that is more or less is going to be your optimal solution. But take it with a grain of salt. So it's not always the case, but almost all of the algorithms use that kind of approach. So now I'm going to show you some complications, what kind of complications we can have in constructing these kind of the cost curves. It is very possible that not the whole domain can be feasible for us. Someone can say that, okay, I don't want my temperature to be above this certain value and less than this certain value because reactor is going to reactor can explode, or side reactions can start dominating my reaction. So we may simply want to avoid these regions. And if this is the case, now taking the derivative and making it equal to 0 won't work for us. So, but you can still see the allegory that if I drop the ball somewhere within this feasible space, it's still going to land on this X mark. And similarly, we can have inequality constraints. We can include these in our models, in our optimization problems. We can have equality constraints, all sorts of thermodynamics and mass and energy balances. They fall under the category of equality constraints. Our cost function doesn't have to be convex. It can have multiple local optima. And as you can see now, if I drop the ball somewhere in the middle, it doesn't necessarily have to land on my global optimum. And that requires more different, more advanced type of approaches for these kind of problems. My function can be simply discontinuous. Somebody can tell us that if the temperature is above some certain point, we may not be able to use some reactor 1, but we may have to switch to reactor 2, and that can create a discontinuity, and that can create a discontinuity in my derivative information. That can also be discontinuous. And also somebody can tell me that I'm not allowed to simply operate within some certain range. So this can create also a different kind of discontinuity. So I'm also showing that because in real problems, we can have all of these or like a combination of different complications. So, but mathematical programming approaches, they all systematically approach these problems. And at the end, we provide a theoretical guarantee that the solution that we find is globally optimum. And this kind of approach, mathematical programming, is not only valid for process design or control problems, and they can simply be, they can span all the way from nano or micro scale problems like material design or protein folding problems, all the way up to process scheduling, planning, or nationwide or worldwide supply chain problems. So this is a very powerful tool to find the optimal solution for our problems. And with that knowledge now, I'm going to show some mathematical formulation, how we can actually formulate our integrated process design and control problem. So the notation is usually like this. We want to minimize an objective function, and this objective function is usually the combination of our capital and operating costs. The capital cost is usually the annualized capital cost. And this objective function is subjected to our process dynamics, which can again include the mass balances, energy balances, reaction kinetics, and thermodynamics. And now, because this is the integrated design and control problem, we also want to include the process control problem, which can include a PID type of controller, the classical controller, which is nice, and it comes in an explicit form, U equals AX plus B. So here we see the first challenge, which is when we take this PID controller and implement it in a design optimization problem, which is typically a static problem, as that we want to just find the best steady state solution for our design. Now we have to discretize our problem, because now we have a dynamic problem, because if we want to include the process control problem, that makes we have to include the time component into our formulation. And with that, we have to discretize the whole domain, and that will create a large scale problem. And the problem is non-convex, which I described what that is earlier. And this non-convexity mostly comes from our reaction kinetics and thermodynamics. And the dynamic optimization problem it's because our objective function and our dynamic model is again dynamic, and that is mostly because of the process control aspect of it. But now another challenge is that if we want to use more advanced type of controllers, like a model predictive control, or it's also known as MPC problem, now the MPC also comes as an optimization problem. And when we incorporate that in my overall optimization problem, now it's going to give me a bi-level optimization problem, and we don't have an elegant way or commercial solvers to solve this class of problem. And this was mainly my research in my PhD. And for the uninitiated, model predictive control more or less looks like this. It has an optimization form of this, and it is operated in a rolling horizon fashion. So at time k or time t, we solve an optimization problem. We obtain an optimal trajectory for our manipulated variables in such a way that it's going to take our outputs closer to the reference trajectory. And after we apply the first control action, we move on to the second or the k+1, the next time step, and we solve the same optimization problem again, get the whole trajectory and apply the first one, and we keep doing that. And that is called the rolling horizon strategy. And here, what I just would like to show is that in the objective function, we want to track a reference trajectory. We just minimize the difference between our set point and our expected outputs. And this objective function is subject to our process dynamics, and all the variables are bounded. And now when we get this model predictive control and integrate in our dynamic design optimization problem, we obtain this ugly looking optimization problem. And here the main challenge is that we don't have an elegant way to solve this kind of a bi-level optimization problem, because now this has an implicit form because of this optimization in an optimization. And in my research, how I tackle this problem is that we can take this model predictive control and we can reformulate it by treating some aspects of the M.Sc problem as parameters. And what I mean by that is I can take the initial states of my problem and my measured disturbances or the set points that I want to reach, and I can treat all of them as uncertain parameters. So now when I solve this problem offline, I can have the entire range of optimal control decisions as a function of these parameters. And when I solve this explicit form now, it's going to give me the exact same optimal solution as the M.Sc would give to me. And we have a toolbox, parametric optimization toolbox, and I'm one of the contributors, which was developed in our group, and I'm one of the contributors of this toolbox. And we can use this to make this reformulation and solve this offline M.Sc problem. And now when we solve this problem, we're going to obtain these maps of solution. And this is basically just a lookup table. All we have to do is whatever the parameter realization is, let's say we know the temperature now, and we have the set point on the second axis. We locate where the parameter realization lies, and we evaluate the corresponding optimal control action. And that is going to give us the exact same decision with the M.Sc control. And now we can use this approach on this bi-level mixed integer dynamic optimization problem, and we can convert this into a single level mixed integer dynamic optimization problem for which we actually have commercial solvers. So we can put this in a commercial solver and obtain a solution. And now I'm just going to show you how this applies to a chemical engineering problem. So this is going to be a benzene-toluene separation distillation column. The decision variables are first the design variables. We want to be able to find the feed tray location and the reflex tray location, the column diameter, and the condenser and reboiler sizes. So these are my design variables. And we consider a disturbance profile, a feed composition, and we're going to be solving for the entire range of this disturbance profile. So it's not going to be just for one disturbance, but because we have the capacity to solve the M.Sc problem for the entire range, I can include this range of the disturbance in my problem. And also my manipulated variables of the problem, which are going to be my control variables or manipulated variables, is the reflux and vapor flow rate. These are for the M.Sc. And by manipulating these, we want to be able to control the top and bottom purity of my distillation column. And to summarize my problem statements, I am given the first principle dynamics of the system, so I can construct my first principle model. And I'm assuming that I'm given the design and operating unit costs, and I want to determine the design of the system and simultaneously with that, the optimal control strategy while minimizing my operating and investment costs. And we're all familiar with the distillation column design equations. We have the mass balances, the energy balances, all the thermodynamic relations, and the trace specifications. And the modeling for this problem was done in the GPROMS environment. If you're not familiar with the software, this is just like ChemCAD or Aspen HYSYS, very similar to them. And this whole system of equations actually give us a differential algebraic equation system, which sort of looks like this because of this differential term. And now we can follow some certain procedure to develop my explicit model predictive controllers, which are going to come with these explicit form, and I can take them and incorporate them in my original high fidelity first principle model. So it will just be a bunch of equations added next to my first principle dynamic model. And I can do this reformulation again by following parametric programming. And when we follow this whole procedure and solve this problem simultaneously, we actually observed an improved efficiency by 17% when compared to the more traditional sequential approach, where we first built the design completely blind to the process control. And the reduction in cost mostly comes from the size reduction in heat exchanging units and the improved energy efficiency. And this whole concept, my research revolves around this whole concept where we use multi-parametric programming for getting explicit and offline expressions for the control and scheduling problems. And at the end of my PhD research, we published the book about these concepts, where we investigate these concepts in further detail. And I would be happy to discuss this if you're interested. And now, lastly, I'm going to briefly talk about my professional experience here at Phillips 66. Well, actually, unfortunately, I couldn't get the necessary permissions to disclose what I would like to show. So I apologize for that. But what I can say is, by using these mathematical programming approaches and these mathematical modeling approaches, I was actually able to model some certain assets of Phillips 66, multiple assets there, and we were able to observe 10 to 30% reduction in costs, and also we were able to reduce the carbon dioxide emissions up to 30%, which is very promising for us, and it is getting a lot of attention across the company. So I'm very happy with where this is going, and there is a lot of opportunities for implementing these kind of approaches across the company. So I'm just trying to say that these mathematical artifacts actually do apply in real life, and I'm very happy to see that is coming to life. And to conclude my talk, I just would like to say that mathematical programming is a very powerful tool for design and control problems. And if we can achieve merging or integrating these design and control problems or different dimensions of our problems, we can improve the efficiency of our processes. And with that, I would like to thank you all for your time. And again, it was very nice to be here. And I would be happy to take any questions if you have any.
Barış, thank you very much. First, I would like to stop the recording. Right.